Cool, yeah. So I'm gonna spend the next half hour or so, and if anyone wants to like nudge me when I'm talking too slowly and want me to wrap my stuff up, then yeah, just give me a pointer, and I can because I could talk about this stuff forever. So brain-inspired artificial intelligence using neuromorphic hardware and algorithms. A lot of people think that neuromorphic is actually a made-up word. Technically, every word is made up, but neuromorphic engineering is kind of like the opposite of biomedical engineering. That's how I perceive it, at least. So biomedical engineering is all about taking some technology, algorithms, hardware, and using it to modulate or adapt or modify some biomedical or biological function, right? Neuromorphic is the opposite of that, in my view. It's more like taking a look at how biological processes, and specifically the brain, how neural processes function, and going in the other direction, trying to take brain-inspired functionality and using it to improve technology. Technology is very broad here, algorithms and hardware. So I've kind of spanned across both of those stacks. Spent a lot of time on the hardware silicon integrated chip layer, and also on the deep learning or brain-inspired deep learning type work. So just to motivate this a little bit more, there's been this trend in going from one-dimensional to two-dimensional over to three-dimensional and higher-dimensional circuits and systems, right? So if we look at the individual transistor layer or the abstraction, it used to be a case of when you apply a voltage to the gate of your transistor, you modulate a single dimension of a channel, right? But then we kind of moved over to FinFETs and over to gate-all-around FETs. I'm not too sure how familiar you are with chip technology, but if you've seen 5 nanometer, 3 nanometer technology nodes, which is what Samsung's language kind of is, where they're scaling down microprocessors such that they fit a lot of functionality into your phones, we're using transistors now, where if you apply a certain voltage, we're now changing the amount of electrons in 3 dimensions. So that's just at the single transistor level. Western Digital have introduced the same kind of thing with memory circuits, where we're stacking up, I guess, layers of NAND flash memory. So your thumb drives are now 3 dimensions. We've got microprocessors. So if we keep on moving up in the abstraction layers, AMD, they just released, what is it, the 3D vertical cache. So they've literally stuck memory on top of their processors. And in doing so, the latency between memory and processor data communication is far, far less. Because with your computers, when you go out and buy RAM, when you buy 64 gigabytes of main memory, that actually the communication between your memory and between your processor is the dominant cost of any sort of computation. So AMD here are trying to kind of circumvent that, say, hey, screw it, let's stick our memory directly on our processor and eliminate that cost. Same thing with image sensors even. Rather than getting an image sensor, a camera, shuttling that information over to a JPEG or to an MP4 file, and then subsequently processing that downstream, again, they say, screw it, let's just directly concatenate an image sensor to a processor. So that's called in-memory processing. And so Sony and Prophecy have been playing around with this. I'm going to talk a little bit more about that in a bit. But now, I've kind of been thinking, all right, so with 3D, there are a lot of challenges that process technologies are facing, right? If you're scaling chips, if you're scaling transistors in that third dimension, you run into, I guess, what's called Denon scaling. Loosely, it's very difficult to dissipate heat. And so heat comes from power, comes from some buildup of an electric field. And then it gets really difficult to keep on driving up the clock speed, which just leads to this negative feedback loop of dissipating just way too much heat, right? So if we want faster circuits, we want to crank up our clock speeds, and that's just heat. If we can't dissipate it, then we can't crank it up. Circuits just melt. So the direction that I'm kind of going in is moving to this 4th dimension. What is the 4th dimension? Time. Let's distribute computation over time. Our brains do that, so it makes a lot of sense to do that in circuits as well. So it's not to say that we multiplex processes. So if I were to say to you, hey, let's do 4 plus 4 plus 2. It's not saying let's split that out over time, split that up over time. I mean, let's literally represent the 4, the 2, the plus in a temporally distributed manner, right? And so it turns out that the brain does that as well. Our neurons are communicating via action potentials or voltage bursts called spikes. So I'm trying to take the computational principles that underpin the brain and integrate them in silicon and into algorithms. So there's a few ways that we've been looking at this, right? So the bottom-up hardware approach, where we do in-memory computing, where we take our processor, we take our memory, we take our sensors, smush them all together, and we get something really nice and functional. And we're also looking at how to use what's called data flow, which is a more computer architecture term. And I guess data flow is this idea that in your generic CPUs, right? Like I said, you've got memory, you've got processors, and they're kind of very physically disparate from one another, so they're wasting a lot of energy shuttling information back and forth. In doing so, you're able to implement a broad set of instructions, right? If I want to open up Microsoft Word, I can do that on my processor, on my desktop computer or on my laptop. If I want to change tack and process a ResNet 50 deep learning architecture, I can do that as well. The idea of data flow is that we sacrifice generality for performance. So I say, hey, I want my chip, I want my computer to only do one thing, but I want it to do that one thing incredibly well. That one thing is going to be deep learning, but you can adapt your hardware such that it is a physical manifestation of the algorithm that you're describing, right? So the brain is that. Like the neural algorithm that our brain runs is just a mapping of whatever the hardware dictates. So that's the idea of data flow. You push data in and the hardware just naturally implements it. So if you do that, you can optimize how your deep learning algorithms run. On the other end of the spectrum, if we look at a top-down point of view of optimization, we can do things via software. So optimizations in the software abstraction include just going towards TinyML. So for the deep learning folk, maybe you've heard of mobile nets. Basically model compression, coming up with ways to reduce the overhead of each of your deep learning algorithms. Quantization, so instead of using full precision, double precision, 32-bit floating point parameters, we squish that down into 8-bit fixed precision integers or binarized neural networks. And then there's quantization and methods to train those. Now, somewhere in between the two, and this is where I kind of sit, is spike-based processing and temporal coding. So distributing all of that information that occurs within, that is processed within deep learning algorithms, spreading it out over time. So at this point, probably doesn't make concrete sense. That's okay. If you attend the workshop later on, I'll kind of go into an excessive amount of detail on what all of this means. But to start with, I was focused on the hardware, the bottom up, designing chips that would integrate deep learning processes before I realized, hey, there's only so far we can get by optimizing hardware alone. Let's move over to software. So we'll see the journey of where my research took me as we go. So to start with, I was looking at in-memory processors using what's called RRAM crossbar arrays. So by the way, we can make this as conversational as you want. If you want to interject, disagree with something, if you're cynical about something, if you have a question about anything that's unclear, don't even raise your hand, just call out to me and we can make this chatty and casual. Doesn't really matter. But yeah, so RRAM crossbar arrays, you might be familiar with DRAM, you might be familiar with SRAM, just different types of memories. So RRAM is resistive RAM. It's more of an emerging exotic type of memory that isn't currently in any of your processors, in any of your mobile phones yet, but companies like Samsung and Intel are working on it. So I was working on using this exotic memory type in order to accelerate deep learning algorithms. And I'll explain what that means, right? So this is just a schematic of these pink dots are, what are they? They're oxygen vacancies, which effectively provide a pathway for conduction, for electrical conduction. If I apply a positive or some sort of voltage, that builds up an electric field, and I can physically modulate the pathway or how those ions are structured, right? So what you see right now, when I form that pathway, suddenly this device, it's got some sort of conductive pathway, and therefore the resistance comes down. So it's kind of behaving like a switch. And if I reverse that voltage, then the pathway disappears. So then we jump to a high resistance. So that's what I mean by resistive RAM. The memory is integrated in the form of the resistance of this device. Now, what's convenient here, and this is distinct to DRAM and to SRAM, if I remove that voltage, right? If I build up that conductive pathway, then I remove that voltage that built up that pathway, the pathway stays, right? So it's a form of non-volatile memory, kind of like NAND flash. So on the other hand, come on, Samson, what are you doing? So DRAM, SRAM, if you remove that voltage, you get, I guess, it's a volatile form of memory, and it's going to forget whatever it's storing. Now, this is extremely important for deep learning algorithms. So if you've played with, I guess, transformers, if you've played with any sort of over-parameterized, ridiculously massive architecture, memory is one of the biggest issues because, yeah, we're dealing with billions of parameters in our language models, convolutional neural nets. So that all comes at a cost because every time we operate on them, we need to shuttle data from memory over to our processor in order to operate on them. So coming up with a technology that can be directly interfaced with your silicon in a way that is extremely power efficient, such as this non-volatile form of memory. And another reason why these RRAM devices, resistive RAM devices, are so kind of neat is because in order to fabricate something like this, you only need to apply a very small voltage to build up a sufficiently large electric field, right? So these are nanoscale thin film devices, so literally very, very, very small. Therefore, when you apply a voltage, because they're nanoscale thin films, the electric field that is built up is massive, and that's enough energy to move these ions around. So we integrate them in what's called the back end of the line. So this is just a 3D cross-section of a transistor of a silicon chip. If you're familiar with how data is routed up and down a chip, we just replace what are called vias, silicon vias, with RRAM devices, also memristors or memory resistors. So they come under a few different names and flavors. So how do they work? Like, why are they a good fit for deep learning algorithms? Right, so now I'm modeling this memristor as a resistive device. And the idea is that we program the resistors, we modulate that conduction or the ions to map across to their respective neural network weights. So if we have a weight of, I don't know, 1.2, just being arbitrary here, and another weight of 0, then the weight of 1.2 is going to correspond to a very low resistance or a very high conductance because they inverse each other. If I have a weight of 0, which effectively clips off any input, so if I have an input multiplied by a neural network weight of 0, then the conductance there is going to conversely be extremely low. So why does that matter? Now, using Ohm's law and Kirchhoff's current law, both in combination with each other, each device is able to draw current. We're effectively able to use the naturally occurring circuit laws to implement matrix vector multiplication, right? So the multiply steps are integrated using Ohm's law. So voltage times conductance equals the current that's drawn. And then because of Kirchhoff's current law, all of these currents are summing across the same bit line or across each column effectively. So in doing so, we're able to accelerate every single deep learning step, which is dominated by these matrix vector multiplications. So your input multiplied by your weights, that's all matrix vector multiplication. We're able to accelerate all of that extremely efficiently. So on the right is a chip that we taped out. It's a mixed signal. So when you accumulate currents, you're operating in the analog domain. That's very different to what all of your processors, all of your mobile phones do. So there's a lot of stuff that's wrong with that. It's very efficient, right? Like if I increase the number of parameters, if I increase the number of inputs in my circuit, then what's neat is that I can literally just add an additional row and it doesn't add any extra time in processing. Whereas with a digital chip, if I need to add an additional input, then I need to add additional cycles. I need to add additional steps to keep on, I guess, processing everything. So the idea is that the time complexity of using this mixed signal analog approach, it does not scale with the number of inputs. So in that sense, it's incredibly efficient. But being an analog signal, the current is extremely susceptible to noise, right? And ultimately, we need to, I guess, plug that current output to subsequent layers. We need to map, or we need to be very careful of how that signal is going to be transmitted to subsequent layers and how it's going to be processed by various activations. That necessitates a conversion step. So we have to go from the analog to the digital domain. So a lot of the benefits in doing that conversion step using analog to digital converters we found that it very much offset the benefits of this in-memory compute RAM approach. So that was quite a massive pain. So I'm not going to go through this stuff. It's just a more detailed look at what that chip is actually doing. But effectively, we did something pretty cool. Accuracy on ImageNet is pretty decent. But the point that I'm trying to get here is that the analog to digital converters to move from analog to digital to the digital domain, that effectively dominated all the latency. All the benefits we got from resistive RAM kind of disappeared once we had to convert values. So where I'm going with this is that the removal of ADCs requires algorithm level optimization. So that kind of started ringing bells, and I thought, hey, the brain and biological neurons operate using spikes. So either the spike happens or it does not happen. So 1 or a 0. That's not an analog value, right? Maybe that's the solution to move forward here. So that's kind of where we're going with this. So knowing all the issues with mixed signal analog computation, I think there was a video that came out on YouTube with like millions of views from the Veritasium YouTube channel. He goes into a lot more detail on this. So I recommend checking that out if this is kind of interesting to you. But yeah, there's what I call the 3 S's, which are very advantageous to what makes the brain useful, and well, at least what we know about the brain that we can port over into chips to make the chips even more useful. So biological neurons interact via single bit spikes. So even though we've got these varying action potential waveforms, in neural coding studies, we kind of simplify that to just be represented as 1. So we've got 0, 0, 1, 0, 0. So every time there is a spike, we just represent that using a 1. So that's pretty efficient. We'll see why that's efficient in a moment. On the other hand, we've also got sparsity, right? If most of your values in a matrix, in a vector, in any sort of data structure, if they're zeros, then it makes a lot more sense to represent that data structure rather than describing it out loud and saying 0, 0, 0, blah, 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 7, 0, 0, 0. It's far more efficient for me to say 7 at position 10, 5 at position 20, right? So only storing position and the position of the non-zero elements is kind of like run length encoding. It's a far more efficient representation of matrices and of vectors that are filled with zeros, right? So anything that's 0 is not occupying space in memory. And so that kind of map, that looks very similar to what the spike-based representation is. So neurons are actually they're very quiet. Most of the time, they're doing absolutely nothing, right? And so if they're doing nothing, then why should they store more memory, right? So we only care about when they spike. Before I go on to that, and another benefit to spike-based processing, right, is imagine if we've got a neural network, just some black box, we've got a bunch of inputs coming in, 1s and 0s. Every time I pass a 0 into my black box and I operate on that 0. So if I want to take 0, I multiply it by a weight, 0 by a weight, 0 times anything is just 0. So I don't actually need to access my memory, which is, like I said, very expensive. So we just skip that step. We see a 0, we skip anything to do with it. We don't even issue the instruction that's associated with that 0. If it's a 1, 1 times a weight is just a weight, right? So it's just a readout step. We don't need to multiply. We don't do anything. We just read out the memory. So for those reasons, 0s and 1s are beautiful. Finally, event-driven processing. So it's the sensory periphery. So our retina, there's a bit of a theory that the retina only processes, it only consumes power whenever there's a change. The same with the brain. If nothing's changing, then nothing's being wasted, and there's no burden on computation. So to start with, I thought, hey, cool. If there's to kind of promote this idea of event-driven processing, let's build a retina-inspired camera. So this was kind of going back to the PhD days, where I'm not going to go into how this circuit operates. Feel free to ask me about that later. But effectively, we came up with a way to use 2 memory cells to flip-flop between each other. So t equals 0, we're programming one memristor. We're changing the conductance of one memristor depending on the light that it's exposed to. So bright light, a lot of programming, like a huge change in resistance. Not much light, then there's not much change in resistance. And they take it in turns in being programmed. So that's MR1 and MR2 here. They're just flip-flopping, right? And in between each of those programming steps, we compare the pair. We pass that comparison into comparator on the right. Now, if the two have been programmed identically, that indicates that there has been no change in our input light, right? And so the output of the comparator is going to be 0 because they're not different. If there is a sufficient difference, then our comparator fires. So we're effectively blocking any non-changing input. And downstream, when we're actually processing all of that, that lets us multiply a whole heap of neural network weights by zeros. So again, this is kind of going in this event-driven paradigm where we only process events, we only process change. So this is extremely efficient for many reasons. So a bunch of circuit stuff, won't go into that. A bit of a comparison. We don't need to worry about that either. But yeah, just to check out what it actually looks like, one of the PhD students that I'm externally supervising at the University of Western Australia, he used this camera to record what's called the jugular venous pressure. So with the intent of reducing heart failure or reducing hospital readmissions due to heart failure. Turns out that senior cardiologists can just eyeball someone's neck, and if there's sufficient distension of your pulse, it indicates that there's massive fluid buildup, and so high risk of heart failure. So using these very sensitive event-based cameras, we're actually able to see this kind of mishmash of, I guess, neck movement. Also, University of Sydney, a couple of buddies over there are using a Sony and Prophecy's version of this event camera for microfluidic analysis. So kind of visualizing T cells through a I guess, honestly not too sure, through like a watery fluidic tube. And you're seeing this in slow motion because what I said about clock speeds. So if you're not processing much, then there's less heat to dissipate. So if what you're processing are mostly zeros, less heat. If there's less heat, that gives you more space to crank up your clock speed of cameras, clock speed of your processors. So if everything's 0, that means our cameras can operate at a much higher speed. And so what you're literally seeing here is, as opposed to what I might record on my phone, which processes every single pixel synchronously, so every frame has to have every pixel, I guess, returning a value. Here, the background is all just dark, it's all black, there's nothing being processed because there is no change. Other than the noise, there is no change. So because of that, we're able to record at a very high temporal resolution. And this here is just super cool. So we didn't record this, but it's just a high-speed laser. And this was done by Sony, by Prophecy. And it's just wild to watch. Like, yeah, seeing a laser in slow motion, everyone's got to see that. So moving forward, and I guess we're going to go into a lot more detail in the workshop, but we've got this need for spiking neural networks because, yeah, we want to be able to get more value out of our chips. We want to crank up our clock speeds. We want more zeros. We want more sparsity. And we've already got these, we've already got event-based or resonant-inspired cameras. So let's kind of translate that into let's pass that directly into a processor, to a spike-based processor. So how does this differ to your conventional artificial neuron model, right? So with artificial neuron models, feed in a bunch of inputs, you scale all of your inputs by a corresponding parameter, and then you sum them together, and that generates some output. With the leaky integrate and fine neuron, it's kind of similar, but the inputs are now just 1s and 0s, right? And those 1s and 0s are represented over time. And if the neuron is sufficiently excited, then it fires. Otherwise, she's quiet. As quiet as anything. So again, the mechanics of it, we'll go into a little bit more detail in a sec, in the workshop. But yeah, input spike at the top, the hidden state, which is the blue line, so that's modeling what's called membrane potential. That starts cranking up, and then it exponentially relaxes back to a steady state value, which is kind of like how our biological neurons work. And once that steady state hits the threshold, then it triggers an output spike. And so here I've just shown, I guess, a recurrent representation of what's going on here. So the voltage or the membrane potential at your next time step is going to be scaled by your current value by some value beta. And so that's just a decay factor, and accounting for an input as well. So that's just the high level mechanics of what we're replacing conventional artificial neurons with these spiking neurons. So yeah, I guess that those of you who may be a bit more astute with, I guess, backpropagation. So to train neural networks, we apply the backpropagation algorithm. And so we're effectively doing gradient-based optimization. We're doing functional calculus to find the best neural network ways to achieve some very niche specific task. To do so, that relies on every single function being differentiable, right? So if you have a non-differential operator in your chain of computation, then no learning takes place, right? I mean, if something is non-differentiable, then you return a value of 0. 0 is scaled by your entire gradient, and so the weight update is also going to be 0. That doesn't make sense, don't worry, we'll go into more detail in a bit. But what I'm getting at is with the threshold operator, this voltage has to meet a threshold in order to trigger a spike. What that means is that this gray dashed line is a threshold, and if the voltage is above that threshold, only then do we see the spike value go to 1. Otherwise, it's 0. Now, so that kind of looks like a shifted Heaviside function. If I take the derivative of that, I get the Dirac delta function. So for all intents and purposes, it's 0 everywhere except this infinitesimal small point where it's infinite. So it's 0 everywhere. Just forget the infinity, it's 0 everywhere. Therefore, there's no learning. So we call that the dead neuron problem, because if we try and apply gradient descent to a spiking neural network, all hell breaks loose, nothing learns, nothing is possible. So this is the hack that we play. We just smooth out the Heaviside operator. We still use the Heaviside on the forward pass, like when we're processing everything, but for the purposes of gradient descent, for the purposes of back propagation, we use the smoothed out approximate gradient. And in doing so, that somehow has managed to fix everything. Even though we're injecting a bit of noise, I think we're quite comfortable with the idea that the world around us is very noisy, the data we feed our networks is very noisy. A little bit of noise from the gradient is quite frankly not a problem. We can handle that. So in doing that, we've kind of taken this, this approach, we've gotten this modular package, and I've got to use a bunch of the graphic design skills that I learned in high school. And I built what's called snnTorch, a gradient-based learning framework for spiking neural networks. It sits on top of PyTorch. It's open sourced on GitHub. It involves some fancy tricks for real-time online learning. If you know PyTorch, then you already know how to use snnTorch just by extension. It's CUDA accelerated, but it's also lightweight enough for CPUs. A couple of startups, and I don't know, maybe you've heard of them, they're currently using it as well, which is kind of cool. So yeah, far right, we're collaborating with Graphcore, who are a semiconductor company who are currently building chips that are specifically tailored for snnTorch, which is pretty cool. And very briefly, we've done a bit of an evaluation. So before we for the workshop, we'll learn how these things actually train, how a computational graph is built, how to code with these things. We'll go into a bit more detail, but we did a few evaluations on multimodal data, right? So we had, I guess, just a regular camera on the left, looking at your right, looking at several different hand gestures. On the left is an event-based camera. And then on the bottom, we also recorded electromyography. So yeah, you get electrodes and that just susses out your muscle movements. Pass these two forms of data into a neural network and just try to train an artificial neural net and a spiking neural net. So overall, the performance for, so Loihi is Intel's neuromorphic SNN chip. MorphIC is just like an academic chip that came out of one of my friends' labs. And in the middle is just using an NVIDIA Jetson Nano embedded accelerator, like a ANN accelerator on a USB stick, basically. So we managed to get marginally better accuracy here, which is actually quite surprising, right? Because intuitively, binarized activations, ones and zeros, shouldn't be better than full precision activations. But the trick here is that we're now distributing that over time. We don't care about the value of the amp, like we don't care about the amplitude of your activation, like you would in a regular neural network. We care about when the spike occurred. And time can't be binarized, time can't be quantized, time just flows, right? So we care about when the spike occurred. So even though we're using this binary form of activations, it's still highly functional because we're representing information over time. More importantly, the energy delay product. So yeah, the ANN for the artificial neural network, that is, the conventional non-spiking case was like 2 to 3 orders of magnitude more or less efficient in terms of energy and processing speed when compared to our approach. So yeah, I'll probably wrap up there because it's been half an hour, but effectively came up with some fancy ways to use resistive RAM memristors in order to accelerate spiking neural nets. blah, blah, blah. I can go into more detail for those of you who might be more interested in memory circuits. But yeah, I think I'll fly through these as well. Now we don't need to talk about that. Cool, couple new ways to do learning, fancy stuff. But yeah, I guess I'll wrap up by saying that neuromorphic computing, it's not a top-down or some bottom-up approach. I kind of view it as more of a middle-out thing if you've watched Silicon Valley. So it's this amalgamation of both, right? And there are a lot of low-hanging bits of fruit there to come up with new ways to do learning that are biologically plausible, the brain might implement, and learning mechanisms that are a very ideal fit for in-memory computing using SRAM, DRAM, RRAM, so all of that stuff. If you want to check out some resources, there's a bunch of links there. Again, we'll go into more detail in the workshop if you want to check that out. I've also got to thank all the people who are listed here. Otherwise, yeah, let's morning tea it up. If you've got any questions or comments, yeah, that's I think it from me. So yeah, this one will be this will be a lot more low level, a lot more casual. So just cut in, interrupt me if something doesn't make sense, and I'll do my best to kind of explain things. I am partially assuming that people have a vague idea of back propagation. If you don't, that's okay. Just like interject, and I'll give you like a high level explanation of it. And I can also appreciate that that 30-minute talk that I just gave, it gave this impression that you have to know hardware to be able to implement spiking neural nets. It's absolutely not the case. This is going to be a lot more algorithmic focus. I think that we'll probably we'll play it by ear. If people need a break, obviously don't hesitate to walk out. But I think once I'm done talking, then I'll just say, if you need to leave, cool. And then so hopefully we'll have time for a bit of a live coding hands-on session to actually play around with snnTorch. Before I move on, I'll probably answer most of the questions in this session. Any other questions anyone had from before? How fast is the camera? Yeah. So the res was 50, the temporal resolution was 50 million spikes per second. What does that mean? Couldn't tell you. Yeah. So 50 million spikes per second. I guess that corresponds to 50, I want to say on the order of millions of frames per second. And it's pretty neat because if you go out and try and buy a camera that has that kind of same sort of resolution, time resolution, it's basically a phantom camera which costs you $100,000-$200,000, whereas that couple $1,000, no worries. It's pretty solid. Yeah. Anything else? Cool. All right, so a little bit more motivation. Back propagation versus the brain. So neural networks are trained via gradient back propagation. What do our brains do? We have no idea, but we're kind of figuring. We've got some theories. We try and take inspiration from it and see what happens. But yeah, so back propagation is the main method for training deep learning algorithms. We run into this bit of a snag. So if you're familiar with I guess the latest, it's no longer latest and greatest, but it's still up there because the numbers are available. So one of the recent fanciest natural language processing algorithms out there, GPT-3, which came out by, I guess, OpenAI, I think it was 1.5 or 2 years ago now. That cost them $12 million just in power bills. So got these huge real estate of just data centers that are just churning away, training this bad boy over the course of 2 months. $12 million. Pretty sure my brain is worth nowhere near that amount. No one is. And yet we can probably speak a little bit better than GPT and understand context a little bit better than GPT-3. So if we actually wanted to ballpark the computational cost of training or updating every single synapse, every single neuron in the brain, we can make a few ballpark estimates, right? So 86 billion neurons, right? Multiply that, well, every single neuron is going to have something like 7,000 synapses, fan out of 7,000. And if we want to simulate the brain with a 1 millisecond precision, so we update all of those synapses 1,000 times per second, we need a computer that can process at 600 petaflops. I think peta is like 10 to the 15, right? 10 to the 15. Now, this might have changed, but 6 months ago, the world's most powerful supercomputer could only operate at 442 petaflops at 30 megawatts. For context, the brain only needs approximately 12 watts of power to run. So there is a little bit of a discrepancy there. So yeah, snnTorch was built with this idea that wouldn't it be nice if we could kind of take the best of both worlds, or we could take these brain-inspired SNNs and merge them with the backpropagation algorithm, because backprop is functional, right? And even if the brain doesn't use backprop, which we don't know, maybe it uses an approximation of backprop, I don't know. It would be nice if we could figure that out. Like if we could at least take the functional advantages of the backpropagation algorithm and apply them to like neuroscience-inspired models of neurons. So yeah, I'm just going to be a bit of a tutorial setup. As I said before, make this as conversational as you want. We're all friends here. So I'm going to start off by talking a little bit more about what's so good about the brain to set the scene. We'll look at snnTorch itself. We'll also look at the language of the brain. So spike encoding. What modality do our spiking neurons, our biological neurons, use in order to communicate with each other, in order to give rise to thought, in order to do things, I suppose. And that's going to lead us to a quantitative look at the leaky integrate and fire neuron, which is a model of biological neurons. Following that, we'll take a more deep learning inspired approach and see how we can optimize leaky integrate and fire neurons using gradient descent, using backpropagation. A little bit on real-time recurrent learning, but that'll be quite brief because I don't want to make this too math heavy, because math is precise but boring. Then a little bit on neuromorphic brain-inspired benchmarks. We've got MNIST, fashion MNIST, CFAR10. What are the equivalents in the neuromorphic brain-inspired world? A little bit more on hardware acceleration of spiking neural networks, but I'm going to stay away from hardware for most of this talk until the end, where I describe what are some tricks that we can play during the training process in order to better fit the hardware that we've developed. Yeah, and some fancy tricks that have helped me train better networks. So, any questions yet? Cool. So yeah, the leaky integrate and fire neuron. So a little bit of repetition, but if you recall, we have spikes coming into this spiking neuron model. So spikes at the input and eventually a spike at the output. So if there is sufficient excitation of this neuron, then it triggers an output. So as we now know, that excitation is some hidden state. And that hidden state is some sort of transient time. It's some form of voltage that hangs on to time in a sense. And it integrates our input until a threshold is met. So what that looks like, just to refresh our brains here, qualitatively, it kind of looks like an input current that comes in, and the membrane potential of this spiking neuron, which is hidden from our current point of view, it's going to integrate and then eventually fire. So we've got the leak, we've got this leakage here. Every time that there's no input, you've got an integrate. So every time a spike comes in, we integrate inputs over time. And once the threshold is met, then we trigger an output spike. This here is the recurrent representation of this neuron. And I'm going to show you why this is important in a moment. But yeah, I guess I can fly through this because I explained what's so good about the brain already. But yeah, sparsity, the fact that spikes can be represented as ones and zeros, therefore less memory access and event-driven processing. So training spiking neural networks. Yeah. Oh, damn. All right, sorry, I would like to apologize to Zoom World for not sharing. Yeah, I had to change the PowerPoint slides. So, and someone has sent a message as well to tell me that I ignored you. My deepest condolences. How's that? I am screen sharing apparently. Cool. All right, so I think that's lucky because I wasn't really showing you anything important that you haven't already seen yet. But from here, right, right? So one of the original approaches to training spiking neural networks was to just train a conventional non-spiking neural network and then convert that to a spiking neural network. So we call that shadow training, or ANN to artificial neural network, spiking neural network conversion. So I'm not going to talk about the details here, just some high-level pros and cons before going more into backprop. But what we see is that state-of-the-art performance on static data sets usually comes from this method. The reason for that is because deep learning is, at this stage, pretty mature. I mean, computer vision is pretty mature. So we're effectively taking all of the benefits that come from computer vision, that come from gradient descent, using methods that Facebook, Google, and all these ridiculously large and rich tech companies are making. All their progress get directly copied and pasted into SNNs. So that's why you're able to achieve state-of-the-art on static data. And the problem there is that static data is not the real world. Like, the real world is dynamic. The real world is time evolving. Everything is constantly changing. So that ANN to SNN conversion doesn't hold up for static data. And it also means that training networks is very simple. We just use what we already know about deep learning algorithms and gain all of their benefits. On the drawbacks here, though, is that by necessity, when we do the conversion, the SNN thus becomes an approximation of the ANN, right? And because of that, your spiking neural network now has an upper limit on performance. And that upper limit is set by the artificial neural network. So my spikes are never going to perform as well as a conventional artificial neural net. That kind of leads to a lot of people being skeptical about spiking neural networks. Additionally, another drawback of this approach is that temporal conversion is now underexplored, right? Another thing, and I don't really care about this final issue, but yeah, I guess it's worth listing there. Now, it's covered up by the Zoom banner, but it's biologically implausible. Our brains are not training an artificial neural network and then subsequently converting them into a spiking neural network. We don't have any sort of, we don't have this pair of networks that are being converted, because that's just, I don't know, it's ridiculous. Like, it doesn't make sense to do that. But having said that, there are several packages out there, some Python packages that do this for you very easily, very intuitively. You kind of just train your TensorFlow or PyTorch network, plug it into like a SNN toolbox, and it spits out the equivalent spiking neural network. And it's still reaching state-of-the-art on like ImageNet type data sets. We don't really care about ImageNet because, again, static images, not really concerned about reaching the best performance for that. It's solved. I mean, not technically solved, but there's a lot of other people doing that. But it's stuck around for like 4 human years. Like, this toolbox here has done the best at ImageNet for 4 years, which is like 400 years in deep learning world. But yeah, so to avoid some of those cons, to avoid that upper limit, upper bound on performance, I'm really interested in, a lot of other people have become really interested in natively training spiking neural networks. So that implies directly applying backpropagation, and there's several other training methods that have come in here as well. So here, we're no longer bound by the upper limit of performance. And depending on your learning rule, depending on what you apply, one could argue that it is biologically plausible. So natively training an SNN is biologically plausible. Now, backpropagation itself probably doesn't take place in the brain in the way that we know. Just the likelihood that our brains are iteratively applying the chain rule and applying gradient-based calculus, this doesn't really make sense. It just doesn't feel right. Like, the vibe isn't there. But there is a lot of research that's going into, what if we replace the gradients with random noise? Or otherwise, what if that random noise was kind of approximated into a gradient itself? If we replaced a bunch of our connections, a bunch of our calculations with randomness, then could that naturally allow the gradient to slip out of the equation? So in that sense, another perspective of training neural networks natively, so that's based on functional optimization. That says, all right, what does calculus tell us to do in order to improve neural network? The other school of thought here is, let's take a bunch of neurons, and we'll go into a bit more detail in a moment. So let's literally take a bunch of in situ experiments on neurons. Let's probe biological neurons from a rat or from a mouse or from whatever species that we want. And let's see how the connection between a pair of neurons changes based on the behavior of those neurons. So in 1997 or 1998, a pair of researchers, what were their names? B and Pu, I think. They discovered that something called spike timing dependent plasticity, right? What they found was that when a pair of neurons that are connected to each other via a synapse, when that pair of neurons, when they fire, so neuron A, neuron B, when one fires and it causes another neuron to fire, then the synaptic connection is going to change. So how does it change? If you can see that neuron A is causally linked to neuron B, such that neuron A fires and subsequently in time neuron B fires, then that connection is going to strengthen. If that causal link is supercausal, like if the spike in time is very close, then the connection strengthens exponentially. The reverse is true as well. If neuron B fires before neuron A, even though we've kind of got this directed connection, then that indicates that there's no causal relationship between these two neurons. As such, the connection, the synaptic strength, is going to decrease exponentially with time. So that's an experimentally derived view of how a network might learn. But of course, in practical experiments, people have actually implemented this biologically derived rule. They've implemented it into algorithms. Surprisingly, it works for basic tasks like MNIST and whatnot. So just basic character recognition, digit recognition. But also MNIST is an incredibly simple task. So basic pattern recognition, it dominates, but the moment you throw in a little bit of some sort of semantic value into your images or into your data, it breaks down. That kind of makes sense because this experimental observation is between pairs of neurons, and it kind of seems facetious to say that a brain is defined by the behavior between pairs of neurons. Just seems very unlikely, right? If we have 86 billion neurons, surely there's some sort of cross-coupled connection that cares about multiple neurons operating together. So a few cons of this, of natively training SNNs, be it STDP, be it backpropagation, it's less efficient on modern hardware. Modern hardware meaning GPUs. So a question came up previously that asked, do SNNs actually perform better on GPUs? No, right? Because with SNNs, we are now forced to additionally process the time dimension, right? That adds computational overhead, and GPUs are not able to take advantage of that. GPUs don't know that I'm operating in the time dimension, nor do they know to skip to skip zero operations. So when my neuron isn't spiking, it returns a zero value. But GPUs don't know that. GPUs don't know that a zero should be distinguished from non-zero numbers. So this benefit only translates over to actual specific spiking neural network or neuromorphic hardware. So this is one of those things that's kind of cast SNNs into doubt. I guess I justify it by saying that it's still worth exploring, right? Like we want to check out if we can find ways to improve the accuracy of SNNs to justify the insane amount of money that gets poured into building hardware. So if we can get some benefit out of SNNs in terms of accuracy, then yeah, then we build the hardware that justifies it. Another issue is that they become very sensitive to hyperparameters. But otherwise, so all of this stuff is, snnTorch is all about natively training spiking neural net algorithms. So I mean, if you want to install it, and I'll run you through it in the final half hour. So for Linux, pip install snnTorch. For Mac, pip install snnTorch. But for Windows, if you're operating on a Windows system, it's also pip install. Just the command, just the system prompt changes. Everything else is the same. So let's talk about the language of the brain. So spike encoding. This is actually like one of those insanely sacrilegious topics that neuroscientists have waged wars about for the past 40, 50 years. So there's like one camp that are all about rate codes. They argue that neurons, information is stored in the spike count or firing rate or the frequency of neuron behavior. On the other hand, the people that argue for the temporal code or the latency code, they argue that information is stored in the precise timing of a spike, right? There's a whole heap of overlap as well. Like you can imagine if a neuron spikes first, and then you kind of reset time, and then it spikes first again, and then you reset time, and you keep doing that, and that kind of in the limit amounts to a higher frequency, right? So there is definite overlap between frequency and spike timing. Let me just check the battery of this laptop. Yeah, let's get this. Is this plugged in? Because I just saw the screen dim, so. Yeah. So in practice, for the purposes of actual processes, so yeah, I'm actually not too concerned about the about what the brain implements beyond. So there is a point where I stop caring about what the brain does, and I only care about what's better for hardware, what's better for computational efficiency. Now, there's pros and cons for both, right? So for rates, that implies that we need multiple spikes in order to represent information. Multiple spikes means multiple memory accesses, which means more power is consumed. Latency or temporal codes only require individual spikes to occur over time in order to represent data. So if you have like a classification problem, you might imagine the predicted class spikes first and all the other classes just spike later, right? One spike per neuron, super efficient. What that actually ends up meaning, resulting in, is that rate codes are able to distribute errors. So if a particular neuron accidentally fires at some time, that's okay, because it's got other spike opportunities to kind of spread that error out, just at a high level. So errors can be spread out over time for rate codes. Latency doesn't really get that sort of flexibility, right? If a neuron spikes at the wrong time, then that neuron is kind of screwed. Your accuracy might be out of whack. So for engineering purposes, rate codes seem to be doing better in our deep learning SNNs, but there are ways to train SNNs to tailor to both. What I found really interesting though was this, let's see. Yeah, so the paper that I've cited down below by Olshausen and Field, they have this really cool paper from like 2004, and it's called "What is the other 85% of V1 doing?" So V1 refers to one of the layers in the visual cortex. So V1 is like an early vision processing region of the brain. And he says, what is the other 85% doing? Because there was a phase in life from the 1950s where people thought that rate codes was all that the brain implemented. But then he actually did some calculations and he realized, all right, so based on the metabolism of the brain, based on the energy consumption of each spike in the brain, in each neuron, there is no possible way that our brains can consume, or that our skulls could dissipate that amount of heat unless only 15% of our total neurons in the brain were relying on a rate code. So that indicates that our brains are definitely not using a rate code alone. There is some latency, there is some spike timing in there. I don't know, we're still figuring it out. And just to confuse you guys a little bit more, interspike intervals are another type of code where, let's say neuron A will fire at some time, it fires again at another time. What interspike intervals look at is the time interval between those two spikes. So I don't know, maybe the interspike interval of the correct class is going to be smaller than something else. Then there is a lot of overlap between all of these concepts as well. Ultimately, we have no idea what's optimal, but that's kind of like the low-hanging fruit out there for interesting research questions on how to train networks using gradient-based techniques in order to encourage neurons to fire in these ways. What might get the best accuracy? And if, let's say, interspike intervals were discovered to have the best performance for whatever reason, then that might indicate that our brains implement that dominantly, right? There's no reason why it's one or the other, but maybe all of these things are working in harmony as well. So yeah, how do we actually computationally process this in a deep learning algorithm? So imagine we have this like black box neural network. everything. So yeah, this is just a random sample from the MNIST data set, just the number 7. We've got options, right? Everything that I've described, you can forget about. Option A is to just take that sample of data, and if it's an image, if it's a static sample of data, you're at liberty to just pass it directly to your network at every single time instance. It equals 0, 1, 2, etc. Like, you can just pass it in, forget about the time dynamics. I mean, you can process your SNN, your spiking neural network, over time, so you get that membrane evolution and your spike timing, I guess, dynamics over time, but your input does not necessarily have to be changing to still get something functional. On the other hand, if you do want to do spike-based encoding, then yeah, we can do that. So this is just the syntax of I'm not too concerned about it because for those of you that want to stick around at the end, I can run you through the code. But syntactically, yeah, we can pass that MNIST sample into this spikegen.rate function, and we get something that looks like this. So the way that this is physically modeled is that every pixel or every feature of your input is just going to end up representing the probability in a binomial distribution. Concretely, imagine the MNIST data set, right? The background is, I guess, just dark pixels, and the foreground consists of bright pixels. So 1s and 0s. Let's normalize it between 1s and 0s. So most of the data that we're interested in is basically 1s, so basically white pixels. You take that one and you treat it as the probability that a spike is going to be generated. So the probability that an event occurs is 1 will lead to a 1. The probability that an event does not occur is just, yes, a p of 0. That's going to trigger a 0 at the output. If your pixel is a perfect gray, a 0.5, something in between 0 and 1, then there's going to be a 50% chance that a spike occurs or a spike does not occur. So that's what you're witnessing here right now. So yeah, all of these white pixels well, I guess light gray pixels, because they're not consistently firing, they're probabilistically firing, and that amounts to a rate code, right? Because I guess white pixels are going to fire more frequently, dark pixels fire less frequently. Alternatively, for a temporal code, this is kind of a case of blink and you'll miss it. But here, bright pixels are going to fire much earlier than dark pixels. In fact, I've just kind of killed all the darkest pixels here. Yeah, that's the number 4 that just kind of triggered very suddenly, right? So yeah, blink and you miss it. So you only pass the deeply informative data at the very start. That kind of intuits why the network might be less tolerant to I guess, latency based processing. But that aside, yeah, syntactically very simple to generate that kind of data just in one line of code, which is kind of neat. Yeah, so this just kind of highlights what I described before. It doesn't really. If you want to go into the more nuts and bolts of this, there are tutorials online that I've written up together, interactive things. So that's cool. So after the input has been passed into your spiking neural network, then how do the output neurons actually respond? So I've described integrating a rate code with your input data. I've described integrating a latency or temporal code with your input data. But that's totally separate to your network itself. That's totally separate to this box, right? We're only looking at this input right here. So the network can also be trained, the output layer of our network can also be trained as a rate code or as a latency code. And that's independent of how we encode our inputs, which, like I said, doesn't even necessarily need to be encoded, right? We're perfectly at liberty to pass conventional images to a spiking neural network, even if they're not varying over time, right? We can pass 0.5s, we can pass 0.8s. They do not need to be spikes. The spiking neural network, on the other hand, yeah, the output do need to be spikes, because that's how spiking neurons can convey, it's how they convey information. So let's just highlight one individual neuron for a second here. Just intuitively, a rate code might only care about so yeah, how do we determine our predictive class, right? So with a conventional neural network, what do we do? All we care about are activations, right? So let's say we've got the MNIST data set, 0 to 9. It's a simple case. That means we've got 10 output neurons. And the output neuron with the highest activation is our predicted class. So here we would expect the 7th neuron is going to have the highest value or the highest output. With a spiking neural network, if we integrate a rate code, then I'm just going to kind of speak in uncertainties because we're still figuring out what's the optimal mode of doing this. But what we currently play with are firstly rate codes. So we would expect that the 7th neuron would fire the most frequently, right? So the most spikes are emitted over how many ever time steps of simulation. So that would be a rate code. Just integrating spike count over a fixed amount of time. A latency code, pretty obvious here. It would look at what neuron spikes first, right? If a pair of neurons spike the same at the same time, too bad. You come up with your own rule as to how to handle that. So yeah, inputs being encoded and your spiking neural network to train in a certain way. They're two separate things. And yeah, you can also integrate interspike intervals and a bunch of other weird rules if you so desire. Maybe you'll come up with your own neural code idea. So a little bit more tangible here. So if I pass this number 3, the static MNIST sample, into the rate code function, and it looks something like this. So all these white pixels are firing with a probability of 1. Then I've kind of got this spike plot measure. So I train this is like a poorly trained network where this plot here, it's a video. I'm hoping it works. It's going to show me a trace over time of every single spike from every single output, from all 10 of our output neurons. So if I play it, cool, that kind of works. So we see that the 3rd neuron and the 5th neuron are firing with the highest frequency, right? And that's kind of unsurprising because this sample of 3 looks very similar to a 5. So in this case, we see that observation that rate codes can tolerate errors, they can tolerate noise, kind of in action, right? So if we had a latency code and we only cared about the neuron that fired first, there's nothing stopping that number 5 neuron from firing first. And once that neuron is fired, then computationally we're screwed. Like the accuracy will then decrease. So here, using a rate by distributing spikes over time, that's not so much of an issue. So that's kind of a high level and qualitative view of the neural code. Yeah.
I have a question. Like these time steps on the x-axis, like when you showed the video, for the number 8, it kind of catched up in the end, like it caught up in the end. So is the neural network changing itself during the time step? Or
no.
Why does it
yeah, why does the 8 come up? I guess that's just part of the lack of explainability of neural networks. So I mean, the number 8, I suppose what we see is that feature-wise, it's kind of facing the same thing where this looks like half of 8. So in that sense, it makes sense why 5 and 8 are there, but you're kind of pointing out at the start, there was no firing from 8. It wasn't until a bit later. All right, here's one thought. Maybe to start with, the 8th neuron just took a bit, it was just a slower process to get it excited. But after that first spike, what we'll soon see is that there's a bit of a reset mechanism for spiking neurons. Every time a neuron fires, the voltage or the membrane potential resets. It could reset back down to 0. It could just be a reset by some subtraction of some value. But what I'm guessing here is that, yeah, we had a subtraction, but it kind of just kept ramping up in a triangular sawtooth type of fashion. So that to start with, there wasn't much excitation. But afterwards, it said, hell yeah, this is pretty sick. Let's keep firing. That's just my run-of-the-mill theory as to why the number 8's firing. It does look like the 3 as well. I'm sure if we trained it a little bit better after multiple epochs, it'd do better. So this was just intentionally poorly trained for like a few iterations just to show a use case where rate codes might matter.
But the rate of the neural network is not changing during this 100.
Exactly, yeah. You're a perfect liberty to mess around with that. Yeah. So the leaky integrate and fire neuron. All right. We've kind of been abstracting away neural networks into a black box. We pass an input, and we've only been wondering what does the output layer do? Now I'm going to look a little bit more in detail at what an individual neuron, spiking neuron node does and how it's represented. Because so far, I feel kind of bad. I've just said, oh yeah, these guys spike, yeah, super efficient, super memory efficient. Trust me, it's fine. Yeah, we need to be a bit more quantitative here. So where did this come from? Where did spiking neurons come from? What's the history behind them, and how did we get to a point where this is how they're modeled and this is how they're trained by a backprop? So this all started back in 1907. So this crazy French dude, Louis Letique is his name. What he did, he was experimenting with frog legs. So there was this live frog, right? And he hacked together this current source, simulated the frog leg, and he timed he measured the relationship between like the intensity of the amplitude of that current and the time it took for the frog leg to twitch. So I'm not sure if that would pass ethics anymore, but yeah, whatever, 1907, anything goes. So he found that the relationship was exponential, right? So as he cranked up that current amplitude, the time of the frog leg twitching was like exponentially shorter. Later on, people started to extrapolate these results, and they made theories of how this exponential relationship looks very much like an RC circuit. Because with RC circuits, if we're comfortable with our electronics, our 101 here, then you'll know that injecting a current source into such a circuit, it basically acts as a low pass filter. So you kind of got this exponential behavior, or this exponential relaxation to a steady state value. I'll show you that. If that doesn't make sense, I'll show you in a moment. Before we get there, biologically, this RC circuit theory is kind of neat, and it kind of makes sense because if we look at the neuron body, so this neuron, this is very, very simplified, right? The reality is we've got this really complex mass of inputs, also called a dendritic tree. So they say that the input of a neuron is the input of a single neuron is actually something like a whole neural network in of itself. It's like meta neural network. But this individual simplified neuron body, right? What is it? What is a neuron body? So what we've got is this ionic saline solution on the inside. We've got a thin insulating bilipid membrane layer that kind of protects that interior from the exterior ionic solution. So in a way, you've got this conductive solution on the inside, a conductive solution on the outside, with an insulator in between. What electrical circuit component does that resemble, guys? It's like 1 in 3 chance, capacitor, inductor, resistor. It's a capacitor, right? So a capacitor it's a metal plate, insulator in between, and it stores charge. This guy, same shit, just, sorry, I shouldn't swear. Same thing, just kind of circled around. So that's capacitive. Now you mentioned resistor. So there is a resistive effect here as well. So as it turns out, the behavior of this neuron is such that when there's a certain equilibrium of ions reached, little gates start to open up and they close up, some higher order complex dynamics that we're not really concerned with right now. That allows ions to travel in and out. So it's not a pure capacitor. We've also got this leakage. That's modeled with a resistor. So if you want actual values, I think that I took some notes here. So yeah, in biology, the capacitance is like, 0.1 nanofarads, and the resistance is 10 megaohms, something like that. So you can literally measure the time constant of ion flow in and out of like charge storage on neuron bodies. So that's kind of cool, I think. So yeah, this is literally what an RC circuit is. If I apply a step current input to this RC circuit, forget the first the linear ODE equations. Let's just go qualitative. If I inject a step current pulse, then the voltage potential across that resistor, across that capacitor, which I've denoted Vmem, meaning the membrane, so membrane potential, is going to exponentially relax towards some steady state value. Let's try something else. Let's kill that input at some point. What happens? What's the downstream effect on the membrane potential? Well, the start of it is the exact same. It starts exponentially relaxing to a steady state, but it's not given the opportunity to reach that steady state value, which is current times resistance. Instead, it starts to decay back to zero. It exponentially relaxes back to zero. Let's try again. Let's keep the area under the current injection curve the same, but half the time period and double the amplitude. What do we get? The exponential increase also kind of commensurately increases, but then the decay is the exact same. Let's do it again. Let's crank it up and half the time that this injection takes place. So we start to see this trend. We're getting this instantaneous seeming rise of current with the same decay rate that's determined by the RC time constant. So in the limit, so this is not physically possible, but in the limit, we'll model this as a Dirac delta input, which is infinitely high and I guess infinitely brief, if I may. In that instance, if we can have this non-physical system, then the voltage across the circuit is going to suddenly jump up. Of course, we can appreciate that this is not possible, but let's just say for computational purposes, it is. In math, we can do anything. Electronics, not so much. But this membrane potential suddenly jumps up and then exponentially decays back to its steady state value. I guess charge is now completed leaking back to ground through this resistor, right? So that is what Louis Lepic, this French guy, kind of came to the conclusion of. He said, hey, this relationship is very much like an RC circuit. It's very much like ELEC 101, which is kind of neat. So if we abstract away the step and pulse inputs and we just apply a single voltage spike, that's what we get. Now, what if we apply multiple spikes, right? Well, the capacitor will just integrate those spikes on top of each other. The response of the membrane potential just sort of rides on top of itself. This should start to look a little bit familiar to what I showed you before. So if I highlight this guy, if I highlight this one instance of membrane potential rising and decaying, and I kind of discretize it in time. So with a time-based neural network or a recurrent neural network, you kind of process the neural network with discrete steps in time. That's what we're trying to do here. Let me see if I can move this guy. No, I can't see. Oh, there we go. Bam. Sweet. So we're discretizing everything in time, right? And so, yeah, if we discretize everything, then it becomes a little bit more amenable to how a recurrent neural network is going to be represented, right? And my mouse has disappeared from this screen, but we're all good, I think. Yeah. So mathematically, this is, I'm going to move this guy again. Mathematically, in the bottom right corner, I think we can kind of infer what's being said. So the voltage at a subsequent step, the voltage at the next step is going to be scaled by, is going to be the present time voltage scaled by beta, scaled by some value that's between 0 and 1. So if beta is, I guess, 0.5, and let's say that the first voltage value is 1, beta times 1, the next time step is going to be 0.5 volts. So it's exponentially going to decay. So 0.5, 0.25, 0.125, and it's going to exponentially decay. Meanwhile, we've also got the input current term as well. So every time an input current is injected, then it jumps back up, but then we keep getting that beta decay going on as well. So what we see is, we see the leak. We see this leakage that's a result of this beta term. We see this integration as well over time. Now we've got integrate, we've got leaky, and we've got integrate. How about fire? So we've got to add this one other, I guess, non-physical parameter, which is represented by this threshold value. So imagine we're measuring the voltage at every point in time, and we've added this threshold. So yeah, again, let's apply that spike train input. Let's see how that responds. So that membrane potential is integrated over time, and eventually it hits the threshold, and it triggers a spike to the output. So what does the output mean? I mean to subsequent layers. Without the threshold being met, without the voltage here reaching that threshold, that particular neuron doesn't transmit anything to subsequent layers, right? And so that's part of why power efficiency is being promoted here. If there's nothing being, I guess, transmitted to downstream layers, then we have sparsity. There's just a bunch of zeros, so nothing is being processed. So now we've captured the fire as well. We've got leaky, we've got integrate, and we've got fire. a very qualitative view of how this has all kind of come about. Capture that, put it into a little node, a leaky integrated via LIF neuron. And so that's an example of, that's probably the prevalent example of the most widely used, the widely yet simple spiking neuron out there. Loads of other neuron models that better capture the more specific dynamics, but I guess we just keep it simple for now. So I'm going to represent that same neuron, but in a recurrent form. If we're familiar with recurrent neurons in the deep learning literature, I'm just translating everything I've described to you into what we know with deep learning neurons. So this top equation, it almost entirely matches what I showed you before. I've omitted the coefficient of the input current. Don't worry about it. And the second equation is just the Heaviside step function, where we compare the voltage against the threshold. If the voltage exceeds the threshold, then a spike is triggered. Then we get a 1. If it's below the threshold, no spiking, right? If we have a low threshold, as you asked, how do we choose the threshold? If it's a low threshold, then there's a good likelihood that the voltage is going to exceed the threshold and there's going to be more spiking. That can also mean less sparsity, more power consumption, but it could also mean more accuracy in our network or more noise tolerance, a bunch of other stuff. We're not really sure. But anyway, let's see the data flow of this neuron. So we have an input current. We apply that input current at some time point. That input is going to contribute to the voltage at the next time step. Then that voltage is going to be scaled by beta, so it's going to leak. So we get that decay there. Then at the next time step, we sum that value, we sum that scaled term with the present time current input. And then again, like we compare it against the threshold. If it's above the threshold, we trigger a spike. If it's not, we don't trigger a spike, and we just keep looping back around until, I guess, something happens. This can be represented as a computational graph. You'll see why this graph representation is important. So again, if I do the same thing, but now unrolled in time, actually, yeah, so I better add this caveat. Left to right, we're moving forward in time. So this here is the neuron captured at one instance in time. And we're just kind of doing the same thing again and again in time. So we apply that input, and it's repeatedly scaled by this beta factor, this decay factor. Eventually, perhaps the input stimulus is excitatory enough or large enough such that the threshold is exceeded and a spike occurs here at time equals t equals 3. So that's all well and good. This can be very easily modeled using one line of code in snnTorch, and we'll get there. But what's being learned, right? I've talked about backpropagation, I've talked about gradient descent, but all we're seeing is an individual spiking neuron node. So in conventional deep learning, what we're trying to learn are parameters or weights, W, right? So that's what we're trying to optimize to get our network to do what we want it to do. In this case, same thing. We have an input. That input here is represented by X. That X is scaled by W. Nothing different to conventional deep learning yet. That scale, that X times W constitutes our current injection. And then everything else is just all the spiking neuron dynamics that I described before. Now, in recurrent neural networks, W is fixed over time. That's what you were describing earlier. Is W fixed over time, or is W evolving over time? So in most deep learning setups, we'll fix W over time. There is absolutely zero reason to do that, other than computational simplicity, other than the fact that that's simply what we do with recurrent neural networks, and we know that it works. So it's kind of like one of those research questions that would be really dope to play with. So yeah, let the weight free, let it roam, let it do what it does, and just keep updating in between time steps. Nothing wrong with that. So yeah, if you're familiar with PyTorch, that there is simply represented using nn.linear. So you just have a linear layer with many weights, many inputs, and then we concatenate that with a spiking neuron directly. Now, once you've generated spikes at the output, well, in fact, like we can replicate this and have additional layers of spiking neurons. At the very final output, we kind of alluded to this before, right? Our output layer of spiking neurons need to do something. We need to train them to behave in a particular way. Now that output, that particular way might mean firing the most frequently. It could mean spiking the earliest, one of those things, right? But we need to calculate a loss. Question.
Yeah, and what's the difference between LSTM model?
Yeah.
Yeah,
Yeah, no, so in a way, they're very similar, right? Like LSTM just has several, it's got its forget gate, it's well, like 4 different gates, and it's represented in the same way. Look, I should actually go the other way.
I think that the structure is very similar to the 4 gate.
Yeah, so that's actually what we're trying to do here. But the point is that we've got this spiking neuron model that was previously represented as an ODE, as an RC circuit. Let's figure out how to model it in a way that looks more like a sequential neural network. This is an RNN that LSTM falls into that subset. And let's train it using the same method, right? So why would you use an LSTM? Why would you use an RNN? Big question. Like, in fact, LSTMs are probably more computationally powerful, but that's one of those downstream research questions that we're playing. How can we tweak this spiking neuron RNN kind of thing in a way that has long-range temporal connections and that it can remember things over hundreds of time steps? But effectively, that's what we're trying to do, right? Yeah.
I have a question. So actually, the state you pass is just it's 0 or 1 is activated or it's not. So in your previous lecture, after it's activated, we'll have the curve. So it's not just the from 1 to 0. So
yeah, that's a fantastic question. So the idea is that the dominant cost. Let me go back here. So yeah, what was just said was that, all right, so power efficiency is obtained because I'm able to have these spikes that are 0 or 1. But the thing is, we've actually added this additional complex, this non-spiking state that doesn't follow spikes, right? It doesn't follow 0s and 1s. So why the hell is this more efficient? That's an extremely important point that I should have addressed earlier. The dominant cost of deep learning is A, memory access, and B, data communication. This hidden state here does technically neither of those things. The only thing that access memory, so when I say memory, I mean where are the weights stored? The only thing that accesses memory is the spike. Spike times weight, that contributes to membrane. That contributes to this membrane voltage. So that membrane voltage is only ever compared against a threshold. That doesn't touch the weights. So that membrane potential doesn't ever need to go to memory. So in that sense, doesn't matter. We tolerate it. Secondly, when you have data coming in, another heavy bit of computational cost is, yeah, moving that data around, trying to figure out what you need to do to that data, getting the right instruction. Is it a multiply? Are we adding to it? What are we doing? This guy has the exact same thing happen to it every single step. Multiply it by data. Have the input as well, but every single time step is purely deterministic. There's never any question about what we're doing to that data. So you can integrate that directly into hardware in order to make it extremely cheap. In a conventional deep learning algorithm, or in even just when you open up calculator on Windows 20, Windows 11, is that what we're up to? Your computer doesn't know what you're about to do to your data. So it has to go to memory, it has to fetch a set of instructions, plucks out the right one that you if you go multiply it and sends it back. In this case, no, you literally put that basis scaling factor into your hardware and you don't need to worry again. So in that sense, it doesn't contribute to the major costs of processing deep learning. Does that make sense? Is everyone okay with that? Because that was a really good point that I should have addressed earlier. So, flying forward, how do we calculate a loss, right? In conventional deep learning, cross entropy loss, mean square error for I guess, classification, mean square error for regression. What do we do with spikes, right? Like, what are the different? There's a lot of variables that we can play with. We can play with individual spikes. We can play with the volt. We can actually play with the membrane potential as well. What do we do? We have time as well. We have time to play with. So I'm going to quickly go through some of these. These are all kind of pre-built into snn.functional. So PyTorch has its own functional module where you can easily integrate cross entropy and various other loss calculating algorithms. So snnTorch has a similar kind of approach here. So cross entropy with rate loss. So what is cross entropy? Probably just, yeah. Do I want to explain that? If you don't know what cross entropy, actually, I'm probably not the right guy to explain exactly what cross entropy is, but yeah, you pass your activations into a softmax and then you find the negative log likelihood of, for whatever reason, it just promotes the predicted class to fire the most frequently. It treats your data, or it assumes that your data comes from a multinomial distribution where one of them is correct and everything else is incorrect. Terrible explanation. Anyway, what the goal with this here is that we just sum up all the spikes from the output neurons, right? The correct neuron it should be maximized. Pretty straightforward, right? In doing that, all the other neurons are going to be suppressed as well. So the softmax, yeah, the natural effect of using the softmax algorithm is to increase the most frequently firing, or the predicted class at the expense of everything else.
Just
All good?
this one.
Oh, yes.
Yeah.
No, it's all good.
This one.
I'll just talk. Alternative approaches are, let's see, mean square error rate loss, right? So we can recast classification as a regression task. What do I mean by that? So we can take our, thanks. Oh yeah, okay, cool. So I've got a bit of a demonstrated example here. So let's say that neuron, so this is like a simple case of 3 output neurons. The top one has 5 spikes, and the bottom 2 spikes, 3 spikes. So we assume that the top one is the predicted class. So yeah, what cross entropy is going to do is promote the correct class to fire the most frequently. So mean square error count loss. We're twisting classification and recasting it as a regression problem. So regression meaning it's something very common with predicting continuous intervals. So house prices. We're not trying to find the correct house price. Well, that is exactly what we're trying to do. We're trying to predict what is the correct house price, but that falls on a continuous number line. We're not trying to distinguish one thing from a series of other discrete options. So what mean square error count loss does is it takes a look at, well, you said it yourself, you determine how many times you want your correct class to fire, right? I might arbitrarily say, I want my correct class to fire 10 times, and I want all of my incorrect classes to fire 2 times. So we're effectively applying mean square error. We're doing regression. Well, in this case, we're doing it 3 times, and we're trying to find the exact on a continuous interval. We're setting what regression value we want, right? So because of the dynamics of spikes and because we're playing with time, there are a lot of different dynamics that there are many options we have to play with. Same thing with membrane potential, right? Like we can apply the loss to the voltage of the neuron itself, that continuous rate, that continuously evolving value. To do that is actually quite popular because there is a stronger gradient signal. If you think about it, let's say we only simulate 5 time steps, so they're a very small sequence. If I update my weights with a tiny update, if I change my weights a little bit, there is a very small probability that the output spikes are going to change. Like my correct class fires 5 times, infinitesimally small update, nothing changes, right? Because I needed to change my voltage by the threshold amount in order to change the spiking, behavior. So mean square error membrane does not face that same problem because it's continuous. Like it's not bound to being 0 or 1. The membrane potential has, I guess, the full continuous spectrum of the number line in order to of real numbers to be able to evolve across. So yeah, I kind of call it micromanaging the membrane potential. We say, all right, we want the membrane potential to be, so if we have a threshold of 5 volts, for example, maybe I'll set the target of the correct class to be 5.1 volts so that we're constantly surpassing the threshold to promote constant firing as well. There's also no reason why we need to set that to be constant throughout time either. So it's up to you. In a case where you want to promote sparse activity. Maybe you set the threshold, maybe you set the membrane to be high at the start and then you ramp it down. A lot of things that haven't really been explored yet. Yeah, don't worry about that. So yeah, we've gotten as far as the yeah. So where am I going with this? Right. So for training this network, right, backpropagation, we've unrolled our computational graph, and now we iteratively apply the chain rule to every single computational step, just in reverse. So you can imagine the longer our sequence, the more values I guess we need to store in memory. Because every single one of these nodes, so every single one of these branches has an associated gradient of the next node with respect to the previous node. And we kind of just multiply them out until we go back and hit the weights, and then we apply a weight update. So as we move back through time, that's called backpropagation through time. And if we're not accounting for time, then it's just backpropagation. So how do we, what are some issues we might face? So here, I said I would try and avoid as much math as possible, but what I'm kind of looking at is one single pathway. So if we look at t equals 3, the rightmost pathway, we see that we've got a loss, and we kind of go back through the spike, we go back through the membrane potential, which is threshold, and we get a current input. So our loss, the derivative of our loss with respect to our weights is going to be a function of each one of these branches. So here, this map here is specifically related to t equals 3, so our third time step. That's all well and good. Now, consider that point, right? I alluded to this earlier, right? So the derivative of our spike with respect to the voltage. You remember that thresholding problem? So if our voltage is greater than, actually no, if our voltage is greater than the threshold, we get a spike, we get a 1, S equals 1. If it's below, S equals 0. If we take the derivative of that, it's 0 everywhere except at the threshold where it's infinite, Dirac delta. So we've been taking the derivative of the Heaviside function and we get 0 everywhere. This term becomes 0. For almost all of time, it becomes 0. And when it's not 0, it's infinite. So the gradient signal is effectively just swamped out. It all kind of messes up. It effectively means that you can't train a network just by using gradient descent alone. So what I said before is that we use surrogate gradient descent. So surrogate meaning approximate here. We use the Heaviside function to generate spikes on the forward pass, but during the backward pass, just kind of smooth it out. Smooth it out, and everything seems to work nicely after that. And the theory is based on what are called straight-through estimators. So Jeff Hinton, god of deep learning, he pitched this in his Coursera course back in like 2012 with respect to binarized neural nets. So if you imagine, yeah, just get creative for a second. So binarized neural networks, they have weights of either +1 or -1. It's binarized, right? In order to determine if they're +1 or -1, then you just train a regular network. You threshold the value. If your weight is greater than 0, kind of clamp it to +1. If it's below 0, clamp it to -1. Now, if you do that, yeah, you run into this non-differentiability crisis. So he just says, screw it, forget that threshold operator. Treat that term that I highlighted as 1. That's where the name straight-through estimator comes from. You just kind of estimate the gradient by completely bypassing that term that screws you over. You just go straight through it. This is kind of similar, but instead of going straight through it, we're just meshing it. Like we're kind of going around it, right? We're using this smoothed out surrogate gradient function instead. And in doing so, everything kind of just falls into place. So the same approach is taken with quantized neural networks. So when you have a really low power accelerator, so NVIDIA's Jetson Nano USB stick that accelerates deep learning algorithms, you can't use floating point numbers. So when you're processing deep learning models on like GPUs and on CPUs, so by default, PyTorch, TensorFlow, all of those are all running with full precision values. So 32-bit floating point representation. So yeah, 32 bits of memory for each weight, in addition to where the weight is stored. With fixed precision networks, well, with binarized neural networks, it's just 1 bit. So 1/32 of the total memory bandwidth is used. For quantized neural networks, then maybe you want to use 8 bits, because we know that neural networks are very tolerant to errors. We don't need that much precision. So we just kind of constrain it to 8 bits. But what we know is that in order to get a really good quantized neural network, during the forward pass, we use floating point representations. On the backward pass, let me reword that. On the forward pass, we use our quantized approach. On the backward pass, use a straight through estimator to ignore the quantization step, right? So quantization is effectively the staircase function. And in doing that, you manage to get the best quantized neural network you possibly can. This SNN approach is actually very much inspired by this hardware constraint. So backpropagation through time involves going backwards. And so yeah, we get a series of gradients. So every single time, so yeah, this weight is constant over time, just in this setup at least. Of course, you're privy to change that. We get a gradient for every single time step. We sum that together, and then that's used to update the weights. So what do we do here? Let's take a look. So previously, I only looked at the pathway of one single time step. Now we're going backwards as well. So we're going from t equals 3 back to t equals 2, and so on and so forth. So if we only account for this connection here, so we look at the connection of, I guess I've written it as v instead of u on the equation on the right. So the derivative of the voltage at the next time step with respect to the current time step, oh yeah, it's quite easy to check that out on inspection. It's just beta, right? So the further back in time that you go, the more betas that your gradient is scaled by. And remember, beta is a leakage term, which means that beta has to be between 0 and 1 if we want to model a spiking neuron model. Otherwise, your membrane would explode exponentially. What that means is that the further back in time the error signal propagates, the smaller it becomes. So on your forward pass, we've got a membrane potential that exponentially decays. But then on the backward pass, you kind of get this dynamic where it's just the forward pass split. So there are ways to take advantage of that. In recurrent neural network theory, we're kind of scared of this. This is called the vanishing gradient problem. Here, I guess we're okay with it for now. But if we're able to smush our spiking neural nets to look more like LSTMs, as was mentioned before, we might be able to get around the question.
Sorry,
Yeah.
I was just wondering, like biologically, there would be like after you reach the threshold, it would then the neuron would go into like a negative sort of charge. You're saying that with like in regards to the spiking neural network, that doesn't apply in this area.
Are you so the question is regarding after spiking the neuron, so yeah, for the listeners at home, after spiking our neuron resets, right?
Yeah, and very
Yep, and you're saying we ignore that, or I'm ignoring that. This actually has nothing to do with the reset mechanism itself. So this is purely related to the spike triggering. So yeah, surrogate gradients are only related to spike triggering.
Yeah.
With the reset mechanism, that we have for that, we set the gradient to 0 because the reset mechanism is also non-differentiable, right? So that's a really good point. I did not include that in the computational graph because it's just easier to look at. But what that will do is every time this spike is 1, it's going to form a connection to the membrane potential here. Yeah, sorry, not used to this trackpad. It forms a connection to this node here, scaled by -1. So we take that spike, multiply it by -1, and I guess that causes a subtraction by 1 from that membrane potential. We do that in the forward pass. On the backward pass, cut it away. That's purely experimental. I've just noticed that it works better when we cut it away. I've also noticed that, and I've got some videos later on that'll show you, that reset mechanism leads to a lot of instability during training. So coming up with ways to reset neurons without some hard heuristically derived reset, I think that could lead to better trained networks as well. Does that answer your question?
Yeah, so you're still doing it mathematically, just by like mathematically decide anyway.
Yeah, exactly. Forward pass keeps the reset. I just haven't drawn it up here. The backward pass, we forget about it. You don't have to forget about it. I've just found that it works better when we forget about it. Yeah. So yeah, it's just kind of neat that we've got this. We can make back propagation through time more efficient just by flipping this kernel, this forward pass kernel. So another thing that I'm playing with is this training method that I've devised called backprop to the future. I'm not going to go into it in much detail, but remember how CP previously asked about online learning, and I was like, oh yeah, you calculate the grade. So yeah, we backprop through time, we store everything. Until we're finished with our forward pass, we have to store everything so that we can backpropagate and calculate the gradient at every time. So online learning and real-time recurrent learning, those types of mechanisms, they offer a way to do backprop through time almost equivalently in such a way that the weights are not fixed over time, right? So how do they do that? So during the forward pass, they add some extra computational steps so that the gradient of one branch, of one time branch, is calculated. So node would kind of gone forward in time and calculate a gradient. At the next time step, we apply some additional operators to that gradient and push it forward in time. So what might that operation look like? It's certainly related to beta. It's like kind of like taking that gradient, copying it, you scale it by this beta factor, because remember, as we move backwards in time, we scale our gradients by this leakage. And you kind of just keep tracking this gradient and keep operating on it over and over again. And but at the same time, we're pushing it forward. It's very high level, and I'm not going to derive it here because it's really, really dry. But the point is that we no longer need to store time traces when we're running backprop through time. That's specifically related to real-time recurrent learning. One caveat here, one thing to think about is that in order to implement real-time recurrent learning, we need a loss at every single time step, right? Now, if we have a target membrane potential at every time step, that's fine. Like if I say I want my correct neuron to be like 10% above the threshold, then every single one of these time steps has a goal. But if I say that I want my correct neuron to fire 10 times out of 100 time steps, I'm not going to know that until the very end. Until my 100 time steps are finished, I'm not going to be able to generate a loss. So what backprop to the future does here, and this is a work in progress. This particular training method is a work in progress in snnTorch at the moment. You use expectations in order to guess what your loss is going to be. So intuitively speaking, forget the math for a sec, intuitively, so we use online learning, we use real-time recurrent learning. But let's say that, again, our goal is for this neuron to fire 10 times out of 100 times. So after like 10 time steps, we would hope for one spike. If our network is behaving equivalently throughout time, on average, it should fire once every 10 time steps. And so we use an expectation in order to guess what the loss is going to be. Now, additionally, what I said was we're pushing gradients forward. Actually, there is a bit of an animation here. So yeah, we're pushing gradients forward in time, we're scaling them by beta, and so on and so forth. But because in this setup, beta is constant, because every neuron shares a value of beta, and it's kind of experimentally derived, then we manage to reduce the memory complexity and just eliminate time from the equation. So real-time recurrent learning, which is the same thing, but without the relaxed beta values, every beta is being learned in a conventional recurrent neural network, that actually has the number, n is the number of neurons, and that computational complexity scales cubically. So that's why people don't use that algorithm, because cubic sucks, and they kind of say, all right, well, we're only dealing with tens to hundreds of time steps anyway, so we can tolerate it. But this kind of lets you just indefinitely run neural networks without having to worry about going out of memory with respect to time. So you just run it forever, and as long as your network can fit in the first instance, then you don't have anything more to worry about. Now, I mentioned STDP, spike timing dependent plasticity. Let me check what time it is. 3:50. Okay, we're doing okay. Spike timing dependent plasticity. So this is one of those observations that kind of, yeah, I'm just going to explain it and we'll see why it's important. So I mentioned that if we have a pair of neurons and they're causally linked, then the synaptic connection between them is going to change based on the spike timing, based on that causality. So let's say we've got a presynaptic neuron, top left, and that's connected in an acyclic graph, or it's an acyclic connection to a postsynaptic neuron, right? So it's directed. If the presynaptic neuron fires, so the top neuron, if that fires before the postsynaptic neuron, you kind of infer that, yeah, the postsynaptic neuron fired because of the presynaptic neuron, right? Like you've got a downstream spike, that spike excited the postsynaptic neuron, and then that neuron fired. In that case, we are on the left, the delta t. The delta t is on the x, the time between the two spikes is on the x-axis, and the weight update, the synaptic update, is on the y-axis. In that instance, we've kind of got like, the way we define it, there's a negative difference in time between the spikes. And so we're on the left-hand side of this plot. And so the synaptic update is going to be positive. So it's kind of like a positive feedback loop. Like if we increase the synaptic weight, then we're reinforcing neuron B, the postsynaptic neuron, to fire in response to neuron A. And you keep on increasing that synaptic weight update. Conversely, if we switch them around and neuron B does not seem to fire in response to neuron A, then we infer that those two neurons are not really linked, they're not doing the same task, and so we weaken that synaptic weight update. Why am I bringing this up? So STDP is kind of broadly recognized as this madly efficient learning rule. So you might notice here that every weight update only depends on its immediately adjacent neurons, right? So if I had a neuron in layer 200, it does not care about these two neurons. It's only being affected by the neurons that it's immediately connected to. Algorithmically or intuitively, it kind of feels like, all right, well, cool. That neuron doesn't need to talk to that neuron, therefore super efficient. Same deal in hardware. One of the dominant costs is data communication. And if I don't need to communicate a value from layer 200 back to layer 1, then that's super efficient. And so this kind of follows the idea of spatial locality. So weight updates are only taking place with neurons that are spatially local, that are directly proximate to that individual neuron. So in hardware, this makes a lot of sense. It's something that we broadly accept in the brain as well. We say, all right, cool. Well, it doesn't make sense for neurons that are not connected to be affecting each other. So that's basically what backprop does, right? We're using a loss and it's updating a neuron, but it's just so super far away from it. It just doesn't feel right. And so on that basis, we argue that backprop is not biologically plausible. Some people disagree, that's fine. STDP is completely biologically plausible, but if we actually use it, it sucks. Like we're just not able to get any good data-driven tasks out of it. The moment I try and do some classification tasks on anything harder than MNIST, it doesn't do anything for us. So one thing that I want to drive home here is that let's say that we're training by backprop through time. We're training a network using backprop through time. Remember how I said the further back in time we go? So I'll highlight this using the laser. So the further back in time that we go here, the more bases that we scale our gradients by. So the further back we go, the gradient is going to diminish exponentially. This looks awfully a lot like that. So what I conjecture, so this is an observation that we found, and I kind of got a bit more formal about it in an archive paper that's been under review for like 12 months now. There's this subtle link between backpropagation through time, which was derived using calculus, using functional optimization, to STDP, spike timing dependent plasticity, which is completely derived from biological experiments. So there's no reason why this link needs to exist, and yet it does exist. So what I kind of am really interested in from a hardware perspective, but we've got to prove it in algorithms first, is that we can hack away at the backprop algorithm, hackprop, and replace a bunch of the more expensive calculations with a spatially local learning rule that we know is efficient, that we know exists in biology. And get something that's approximately like backpropagation. So not going to derive on like what we've done, but again, this is something that's currently being worked on in snnTorch, where we integrated STDP into it. But because it's being run in the context of a PyTorch framework, it's also got gradients being calculated, and so we can use STDP together with backpropagation. That's one of those things that we're just fumbling around in the dark, trying to see, hey, can we get something meaningful out of it? So very, very open research question here. So that's kind of like what I want to go through in terms of training neural networks. From here, it's just a little bit more palatable, I'd say. So some of the neuromorphic benchmarks include neuromorphic MNIST, where this guy from Intel literally got one of those event neuromorphic retina-inspired cameras, and he just kind of moved it around in front of the entire MNIST data set. He just like wrote up a script to get like a tilt and pan automated tripod to film a computer screen that displayed every single sample from the MNIST data set, and he just recorded it one at a time. So that's one of the kind of crappier neuromorphic benchmarks that we have. The DDS gesture data set comes from IBM. It's a little bit hard to see, but it just consists of 11 classes of hand gestures, right? So this here is like a clockwise arm rotation. There's other stuff like air guitar, peace sign. Those are some of the classes that are trying to be classified. Another cool data set is the spiking Heidelberg data set. So this is like an audio version of MNIST, where someone's recorded themselves and said the numbers from 0 to 9, few different voices, male, female, variety of ages, and they've passed this through a cochlear model of the neuron. A cochlear model, each model with 700 neurons in it, and they've just basically converted this audio signal into neurons firing. And so trying to classify what digit is being uttered out loud based on this cochlear model is kind of a cool way to assess whether or not your network is performing all right. So with this, I forget what number this is, but either way, you can kind of see different frequencies based on different words. So if I say the number 8, so that at the end generates different dynamics, different frequency dynamics from various neurons. So it's all kind of neat. Like it's more neuromorphic than MNIST, right? So we like to look at that. A trick that we also use. So another major point made in that paper before, what's the other 85% of V1 doing? In addition to power consumption. So why are rates codes not biologically plausible? So I mentioned that it's just really expensive in terms of power and heat dissipation. Another reason against it is, let's say you're out in the wild, you're in a forest, you hear a lion roar, crap, better run. Now, neurons fire on average at like 0.1 to 1 hertz. So that's 1 spike per second. And well, one spike per second to 10 seconds. Now, if you hear a lion roar, you want your reaction time to be much, much faster than that. So in terms of what humans and frogs and just a variety of animals can do in terms of how fast they respond to external stimulus, it doesn't make sense that we have to wait 10 seconds for multiple spikes to be triggered before we run away from this lion. We probably die. So this idea is that it's still possible to implement a rate code in a network, but rather that rate is distributed across a population of neurons. So with MNIST, I said we've got 10 output neurons. Now scale that up. Let's say we've got 100 output neurons. So then we take 10 neurons per class. And in that case, we could simulate this spiked neural network across 1 or 10, across a very short number of time steps. And we can accumulate spikes from far more neurons, which also helps with improving training convergence. So yeah, so it's kind of like just duplicating that computational graph and making them all run in parallel. That's like one of those tricks that has really helped with overcoming the dead neuron gradient problem. Let's see what time it is. I think I'll probably actually just forget about, I won't go into this stuff here, but let's see. So yeah, we did a bunch of stuff playing with binarized spiking neural networks. And again, because we're training networks over time rather than in terms of amplitude, we're not binarizing time. So this is a very, very memory efficient way to integrate spiking neural nets. Also some neat hardware tricks that we've played with. We alluded to messing around with thresholds and playing with hyperparameters. Now, one really quirky thing that I want to briefly bring up is that the more spikes there are, the, I guess, less efficient your architecture is. So what I was actually able to play with was regularization and penalizing your loss based on spike activity. So you've got your mean square error, your cross entropy loss. In addition, you add an extra term that just sums up the total number of spikes. And so you discourage your network from firing frequently by trying to reduce that number of spikes, right? So it's kind of like, yeah, with regularization, L1 and L2 regularization, you penalize your network for having weights that exceed the number 1 or just from going out of bounds. Similar kind of deal, just with less mathematical basis and just more empirical motivation. We're just trying to decrease the number of spikes. What that means in hardware is that when we stream spikes in, well, there are just less spikes to process, therefore more efficient. So currently working on an FPGA implementation to accelerate these bad boys. Accuracy degradation is pretty minimal. Of course, you take some hit when you convert your weights into binarized values, but of course, because of time being the key component here, it becomes significantly amortized, and we don't need to worry about that as much. A bunch of other stuff we don't need to worry about. Some ongoing work with GraphCore. We previously mentioned that training spiking neural networks is not efficient on GPUs. So GraphCore has released intelligent processing units. So there are a few features in IPUs that are really well suited for spiking neural nets. I'm not going to go through what these benchmarks mean, but it's kind of like our way of trying to use GPU-like architectures in order to make training SNNs a little bit more efficient. Happy to go into more detail one-on-one with you. Now, everything that I've described is available in far more detail on some online tutorials, very well documented, and I recommend checking that out. So I'm going to give, like, I don't know, 10 minutes of questions and discussion. You're more than welcome to bounce if you want. After that, we can spend like, if you want, 20 minutes just doing some live coding where I actually show you what snnTorch does, what it doesn't do, train a neural network in front of your eyes. So yeah, any questions? I think that's it from me for, I guess, other than the live coding session. Cool, yeah, any questions? Yeah.
Thank you, first of all. But that calculation you showed us, does it affect the MSC count loss?
What do you mean by that?
You couldn't see the slide.
Oh, yeah.
You couldn't see the slide.
Yeah. So for the Zoom listeners, the question is related to the link between backpropagation through time and the mean square error count loss.
This one,
Yeah.
Basically, now what you explained here is clear, but I'm not sure how do you relate it to the MSC count loss? Because that's not the normal loss, I would say.
Yeah, okay, I understand what you're saying. Okay, so forget this loss calculation for a second. Now, imagine that you have, imagine we've got 10 neurons at the output. That connects up to an additional node that sums up the total number of spikes. Actually, every one of those 10 neurons goes to that same node to generate one single loss. That loss is the mean square error count loss. And then when you apply backpropagation, everything flows back from that one single node. So here, we have a loss flowing back from every single individual loss. Like we have many different losses that are all being summed together. Whereas an MSC count loss, we wait till we count up the number of spikes and then we sum them together.
Is it more efficient or not?
Not sure. The question is it more efficient? I initially said not sure. I think it makes more sense for it to be more efficient. Right? So with cross entropy loss, we calculate a loss at every single time step. We have a target at every time step. With MSC count loss, we only have a loss at the very end. Therefore, in that sense, we only have a spike contributing, we only have a value contributing to a loss whenever there is a spike. Otherwise, there's always going to be a contribution. So it's kind of like, I would almost, they're not equal, but I would say in terms of computational complexity, I would equate them to one another, but you're just cutting the connections wherever there is no spike. Now, GPUs are not going to make that more efficient because they don't know. but I guess that it could lead to more efficient if you have hardware that is aware of it. That's just pure guesswork on my behalf, right? I think it makes sense. Yeah, any other questions?
So can I ask a question that you have mentioned that if we do some classification, we can have channels for closing, like there are 10 classes. And actually, machine learning, you can reduce the channels to 4 nodes. You know, finally, 4 nodes can represent 16 combinations, right? But in spiking order, can we also do that because it's just context spike.
Is what you're, so yeah, let me make sure I understand your question. Is what you're saying, in a conventional neural network, if we have, say, 16 classes, we can condense that representation into 4 nodes, into 4 output neurons, and we can encourage those 4 to have a binary representation. So the number 10, for example, would have neuron A fired 0 times neuron B, 1, neuron C, 0, neuron A, 1. So it's 1, 0, 1, 0, and that's 10. Is that what you're saying? Yeah. Does anyone know whether or not we want to actually do that? Whether or not we want to train a neural network to encode outputs, so non-spiking, by the way, as a binary representation? No. So the answer is no. You typically do not want to do that. So firstly, if you actually try that, your network will just not perform as well. Why? Because the binary encoding of data has nothing to do with what the input data is. So if I encourage neuron C to fire for both for all of my even numbers, right? So for even numbers, your second position of a binary, of a 4-bit binary integer is going to be always active. There's no reason why that neuron should be active for number 2, for number 4, number 6, number 8. It makes more sense to have a neuron that identifies maybe loops. So the number 8 or the number 3, which kind of looks more similar. It makes more sense to represent neurons based on their features, based on their input features, rather than something arbitrary like binarized representation. I understand that reducing the number of neurons makes it seem more efficient, but it kind of breaks this. There's no reason why we want to train a network other than that efficiency. There's no prior that says that this neuron needs to fire X number of times because that's what's mathematically efficient. That's not a really formal explanation, but yeah, but for deep learning, we don't want to do that already. For spiking neural networks, could it be? Yeah, it is possible to do that, but I would say for the same reasons, it's something that you probably don't want to do. Yeah. Question. Yeah, we'll go. Yeah.
It's not a question, just a conclusion. So if you have more time steps, so it means you have chance to have more choice. It means you have more information. So as a result, you have better activity. So but if you think about the hardware, so it means you have higher latency, which is not true. So from optimization perspective, I'm thinking about this is a two conflict of decision. Have better spiking elements such as what less information. Is that correct?
Yeah, absolutely. Yeah. Everything's always, in electronics, everything's always conflicting. Like you're just trying to find the Pareto optimal value of power area. Yeah. If you want faster, you need a bigger transistor with a bigger drive strength. But then that means more area. So yeah, everything is always conflicting, and deep learning is no exception. Yeah. Question.
Regarding the architecture that you use for training, I asked that how many direct fiber outputs that you use in training. For example, in the convolutional, you have backslice, then inside.
Good question. So I'll break this down into 2 parts. So first part is every neural network architecture in a deep learning perspective, convolutions, ResNets, fully connected layers, they can all very easily be translated into spiking networks. So in practice, I would do a convolution. I would have an input that it could be convolved. The output of that convolution is going to constitute the membrane potential of the value, and that membrane potential is thresholded, and then you get a spike. So we very frequently, actually almost exclusively, use spiking convolutional networks. So this computational graph, just replace the input with a convolution, and then it's the same thing. So all of the hyperparameters from your world translate directly over to here, in addition to spiking neuron hyperparameters. Beta can be a hyperparameter. Whether beta is the same globally for every single neuron, or if it's the same for every layer independently, or if it's individual for every single neuron, whether it's learnable, whether we track the gradient like in a conventional recurrent neural network, well, then maybe it's a parameter, maybe it's a hyperparameter. The threshold can also be a hyperparameter. What else have we got? That's all I can think of off the top of my head.
Okay, so in this regard, then, I mean, does it have the main effect in the by computational process?
Right. So when you're doing when you're doing a hyperparameter sweep with additional hyperparameters, absolutely. It's computationally expensive when you're trying to find the optimal architecture. Yeah. Once you've found it, once you take that and put it onto a neuromorphic circuit, then you're fine.
So I mean that is more complicated than the simple convolution or nothing.
100%. Yeah, you're adding extra feet. Yeah, you're adding. Yeah. So at the start, I said that one of the drawbacks of training using backprop is it's very sensitive to hyperparameters.
So
yeah.
It means that it has this low convergence.
Oh yeah, absolutely. At the moment, SNNs have, there's a caveat to everything that I've described so far. As much as I would love to say SNNs are the future, there's a whole onslaught of problems that we have to overcome, right? Because we're not using the precise gradient anymore, we do have slower convergence than conventional neural networks. Additionally, if we were to train, we're not able to train networks, we're not able to train SNNs that are as deep as conventional, so the VGG 50 type architecture or ResNet 50 type architecture. If I wanted to do that with an SNN, the cost of parameter sweeping across all of those layers, no one's done that yet. Yeah, we're doing 18-layer SNNs just fine, but we're still trying to figure out I guess we still need like a timing curve for figuring out optimal weight initialization techniques for SNNs. Is lagging 5 years or so. Any other questions? Yeah.
I think this is going back to that first question again, but I didn't understand something. Yeah, but I'm wondering, like, you've got the zeros and the ones, and like I'm thinking back backwards, that processing kind of thing. So the one would be equivalent to something else if it was raw data.
Yeah.
So where is that back to processing that kind of helps you figure out what that threshold is?
I completely understand.
I'm just like, because there will be like cutoffs, or like when the threshold of the threshold of the node size, for example.
Yeah.
Who defines what the one equivalent is?
Oh, you do.
Okay.
Yeah, the question is who defines where your threshold is for input data or for even your spike neuron.
So you know what you're interested in.
Yeah, that's like a human injected prior.
Yeah.
Having said that, it's nothing that demands you to encode your inputs anyway. If anything, encoding your inputs as spikes, for converting MNIST, converting whatever to spikes, is just a form of lossy compression, right? So if anything, whenever I'm training something, I'll forget about input encoding and just use raw data. Then I'll compress it into spikes, because then you have the argument that, I guess, if you have lossy compression, then if you develop a sensor that only fires every so often, then that's going to be far more efficient. So you kind of want to know, can the network tolerate that compression? If so, with rates, I found that with simple tasks, no problem. With latency, it sucks. So but biology uses, like, we know that latency is used in biology, so it's kind of the question of how can we harness that? We're not sure yet.
So it's just trial and error to find out what is the sort of question.
Just like deep learning. Yeah. Is there another hand? If not, I'll let you guys go, unless you want to stick around for like some Google Colab live. Actually, everyone put your hands up. Everyone put your hands up. Put them up, put them up, put them up. Put them down if you just want to bounce and go home and chill out and not code.
What's the regression example if you have in the code? Because I couldn't really get how you can use the MS calculus and the rate code for regression problems.
Yeah, let's do that one-on-one. I'll do some coding, like just some quick on the fly coding, and then I can just get a pen, get some paper, and run it with you. Yeah, if you guys need to go, that's me. Thanks for coming down. If you want to stick around and watch me spend a few minutes on Colab just to show you how to train a network on the fly, then stick around. Thank you. Well done, Jason. Yeah, cool. All right, I'll exit the PowerPoint slides. For those of you listening on Zoom, is anyone even left there? No, all good. Cheers. Let's see. All right, so are people familiar with Google Colab here? Sorry if I'm exposing your Google search history. Yeah, is there anybody here that has used Google Colab before and knows what Google Colab is? Okay, a few people. So if you don't, it's bloody beautiful. It just makes life so much easier. It gives you like this pre-packaged Python environment where you don't need to worry about, if you're not very familiar with Python or familiar with setting up, I guess, coding environments, it just makes life so much easier. Like everything, like if I want to import PyTorch, import torch, whoops. Yeah, I just hit import torch, done, other than the error that's probably going to be thrown. Not just that, but you also get limited free time on GPUs. So yeah, you just go runtime, change runtime type, hardware accelerator, GPU, and then free GPUs to accelerate your neural networks, which is pretty dope, I think. Let's see. So I have a little bit of template. Now I also have like a pre-filled one because, so yeah, programmers spend like 99% of their time Googling and on Stack Overflow. The remaining 1% is actually coding. So there is no way I remember all of my own syntax. So I have like a pre-filled notebook to refer to. My man, we've got a mouse. You can see me struggling. All right, so yeah, if I go shift enter, then yeah, just running a few preliminary stuff. Let's see. So yeah, to start with, just pip install snnTorch, just like I said before, pretty easy. So we're importing a few libraries that are useful. So snnTorch is SNN, spiking neural network, of course. There's a few utility functions on this line. Torch is just PyTorch, so Facebook's deep learning framework. And then for plotting a few figures, matplot and lib. Now, before we go forward, before we actually try training something, then we want to load in some data that can actually be played with, right? So just to keep things quick, easy, and simple. Ooh, Zoom is not pretty to this data. Sorry. Let me share my screen. All right, so for people in Zoom world, I imported snnTorch. Sorry, installed snnTorch, imported a bunch of packages. Now, a bunch of training parameters. So, of course, to make things more efficient, we use batches of data. We want to pass in a whole heap of data in at the same time. So, batch size of 128 is pretty standard if your memory can cope with it. Subset. So, I'm just dividing down the data set by a factor of 10 just because I want things to. I don't really care about hitting state of the art in front of you guys. I just want something quick and easy to show off. So then, yeah, to download data sets, just don't worry about all of this. Like if you want to follow along, just go to snnTorch tutorials, just Google that, and you'll be able to find something. So let's take a look at one of the samples of the data. So the number 4 here, right? That's just a raw sample from MNIST. Now, previously I mentioned the neural code. So how can we convert that into spikes? So within snnTorch, there's a module called SpikeGen, Spike Generator, I guess is what it stands for. So if I want to convert it to spikes, so spikes are occurring over time, so I need to define how many steps I want to simulate that over. Can everyone read that, or do you want me to like zoom in or something? Is that better? Yeah, sweet. So yeah, we'll do it over 100 time steps. Then spike data, I'm going to take one sample of data. This mouse is finicky. I'm going to take one sample of data hit, and pass it into SpikeGen. So if I want to convert it into a rate code, then I'm going to pass in data it, num steps equals, I guess, 100. Let's see if I've got the syntax right. Cool. So spike data now holds a single batch of spiking data that's converted mnist into this spiking mnist kind of form. So let's take a look at the size. So the size of this tensor is 100, so that's 100 time steps by 128, which is our batch size, by 1, because the black and white image, we only have one channel. 28 by 28 is the length and width of this data. So if I want to actually show one sample of data, I want to index into one of these single samples from that batch size of 128. That's what I'm doing here. I'm just plucking out the first sample in that batch, and I store it into what's called rate sample. If I want to show you the animation, then just some boilerplate code. Ooh, that was a bit intense. Yeah, it looks something like that. So we've got probabilistic firing based on the pixel values. So one thing that we can also do, because mnist is all white, like it's mostly black and white, right? So we can change the gain of the input. So if I want to suppress spiking and get a bit more sparsity, then I'll set my gain to be like 25% and do the same thing here, right? And so we're going to get a little bit less spiking. Yeah, so it's a bit more sparse. Now, similarly, we can also change rate to be latency, and there are a variety of other encoding methods as well. So latency, nope, my typing is not great. Latency, let's see, I guess num step stays there. Also, just there's a function called normalize. Sorry, there's an argument called normalize, which just, I won't explain what it means, but check out the documentation if you're curious. But the point is that it takes one line of code to encode your input data into spikes. So yeah, like I said, blink and you might miss it. So at the first frame, we've got spikes, but then it just disappears because that's all the white pixels that it's firing at the start, and then it's kind of like your grays and your other values. So that's all well and good. Let's actually take a look at spiking neurons, right? So that's encoding inputs that are pre-existing. So if I want to create a spiking neuron, then let's see. So SNN contains all of our spiking neuron models. A variety of them exist. Leaky is the leaky integrate and fire neuron that I've been showing how to use. So beta is that decay factor. If I set beta to be 0.1, then we decay very quickly. So at time step equals 2, the value of your membrane potential is going to be only 10% of the previous step. So let's have a bit of let's have some dynamics that last, right? So we can also mess with the threshold, a bunch of other stuff. I'll just stick to this one single line initially. So I want to track all my values over time. So I'm creating a couple of lists. So one list for my membrane potential and one list for spikes. And we're going to store everything over time. So we've just initialized this empty list. So if we want to, and now we want to also create the inputs into our spiking neurons. So here I've said, let's just set an input current of 0 amps. So let's see what happens to a spiking neuron without any input. How does that behave? Just based on what I've said so far, it should just decay. If it starts at a non-zero value, it'll exponentially relax. So we want to verify this. So my input is just going to be torch.0 is 0. So sorry, torch.0 is 1. So that just means we have one value and it's 0. And that's part of the PyTorch tensor. Mem, what do we do? Let's say torch dot. So if I set it to be greater than 1, then it's immediately going to fire. I don't want to do that. I just want to set it to 0.8 for now, just for a demonstration. So I'm going to start the membrane potential below the threshold at 800 millivolts. I'm going to have, ooh, something happened. Oh, that's right. So I take that So I want a torch dot, I want a 1, I'll multiply it by 0.8 instead. And let's see if I can remember how to code this together. So if I did it once, so yeah, if I need to loop around this using a for loop, so 4-step in range num steps. This means that we're just iterating over the same block of code over and over again. So what happens here? So the output of my spiking neuron is going to be 2 things: membrane potential and spikes. So let's just say SPK for spike, mem for the membrane potential, and I define my spiking neuron here as LIF, leaky integrated fire. LIF is going to accept 2 arguments, the membrane potential and the input. So I guess this is some documentation with a complete example here. So we have an input and then membrane potential. So my input was X and my membrane was mem. So that's going to keep on overwriting the membrane at every step. So memrec, I'm going to keep track of the membrane potential over time. Spike rec dot append. So let's see what happens here. So that's done. Now I've already pre-written some code to plot this function. So yeah, like I said, we start with our membrane potential and it exponentially relaxes to some value. Now let's do the same. Let's do the same thing. This time I will apply an input current injection of 0.25 and my membrane will be initialized at 0. So we do the exact same thing, the same for loop. We're iterating over this code 100 times because we have 100 steps of time, and that's very quickly done. So it looks something like this, right? So we exponentially start to relax towards some steady state value because our current injection is it's a constant step current. But instead of reaching that equilibrium point of current times resistance, it's instead hitting the threshold, resetting, and just repeating, right? So that's what that looks like. And this bottom row are the output spikes. In a neural network setup, that output is going to be streamed to your next layer. Every moment in between where there are no spikes, nothing is being streamed to the next layer. So let's get a bit more excited. So training a spiking neural network. We know how to build one neuron, but in order to train a spiking neural network, we need to combine it with torch primitives. So linear layers with convolutional layers, whatever the hell we want. And we concatenate them with these spiking operators. So a little bit of boilerplate code, torch.nn. NN is just the neural network library. Define the network. So beta, what can beta do? Let's just set it at 0.8. Spike grad. So remember how I mentioned surrogate gradients? So you're expected to define that yourself. So there's a plethora of different gradients that you can use. Sigmoid. So remember how there was a heavy side function, we kind of smooth it out. A sigmoid. In the literature, people use what's called a fast sigmoid as well. There's plenty of options, but yeah, I just go surrogate dot fast sigmoid. I guess a whole heap of them have come up for me. Damn, done. That's easy enough. Then what I will do is construct my network, right? So I'm saving my network into this variable net. Now PyTorch has a function called nn.sequential, which lets me just define a bunch of layers, separate them out by commas, and whatever input I inject is just going to flow through those layers, so it's a really convenient representation of a neural network. So we'll start off with a linear layer meaning a dense neural network, a dense layer. So the number of input features is 784, which is just the MNIST dimensions. We can have a hidden layer size of 100. So our first layer is just an all-to-all connected layer. The next layer, so once we've done that, we then treat that output as our current injection. That current is injected into our spiking neuron. So that is going to look like this. So snn.leaky, beta equals beta, spike gradient, spike grad equals spike grad. So I'm basically passing this gradient here into the same named variable. I'm sure I could use better practice. Don't worry about this boilerplate, but this is just a little bit of extra stuff. Hidden is true. Then if I want another layer, just so we have like a 2-layer network. nn.linear 100, that can go to 10 output neurons, and then we concatenate that with another leaky layer. So beta, beta, exact same thing, spike grad, spike grad. Don't worry about these extra arguments for now. Then we set output equals true, just to tell this network that, what's my error here? My man. All right, let's see if this works. Unexpected end of field. Oh yeah, maybe I haven't defined it. So device lets you, I don't think that was it.
Another bracket.
Oh man. All right, there we go. So we now have a network. So we want to define our forward pass. In the interest of time, I'm just going to copy paste what I've done. Whoops. Just going to copy paste what I've done before. So I've got a forward pass where, we generate the list of spikes. I've got to reset my network. So yeah, every time we do a forward pass, of course, the membrane potential is evolving. So I want to reset the membrane potential at the end of every simulation. So that's what utils.reset does. We do the same for loop to iterate over time steps, and then we return the total spikes. So that's that function. Then next, I want to optimize, I want to define my optimizer and my loss function. Optimizer, we just use the atom optimizer, very robust for recurrent neural networks. And we're also using the MSE count loss. So your prayers have been answered. I'm going to use the mean square error count loss. And what this implies is that the correct rate needs to fire 80%. Sorry, the correct neuron or the predicted class needs to fire 80% of my total time steps. That is 80 spikes out of 100 time steps. I'm also going to set my incorrect neurons to fire 20% of the time. For some period of, for a few months, we thought that if we have incorrect neurons also fire a little bit, that's going to avoid things like vanishing gradients and for signals to kind of die. In reality, we haven't really noticed any difference, but just showing that here because I guess I can. And the training loop. So what's going on here? So let's go 10 epochs. We use 25 time steps, so a pretty brief period. And then we iterate over those 10 epochs, extract our data from our data loader. I guess I haven't defined device. So device just lets you, if you set device to be CUDA in a string, then that lets you take advantage of Google Colab's GPUs. So I then pass my data into the forward pass function. So previously, I've already defined my forward pass. I need to flatten my data because remember, MNIST is a 28 by 28 sample of data. So I need to unroll that because I'm not using a convolutional network. So the fully connected networks, flatten it to 784, smush that into your network. Then I calculate the loss value. So loss function, that's just the mean square error count loss. I pass in all of the spikes. I pass in all the spikes from every single output neuron, and then I compare it to target. So that's all taken care of in the background. If we have time and if you want, we can go into detail as to what that function is doing exactly. Then we have our optimizer, bit of boilerplate. You just have to do it in order to update your weights, and a few little functions to spit out what my accuracy is. As a caveat, I'm assessing this on my training set. So of course, that's terrible practice for neural networks. You don't want to do that. Epoch 0, but that's after the first iteration. So basically, immediately, we see very good performance. But of course, MNIST is super easy, and I'm also assessing on the training set. If you want to actually report values, you do it on your test set. You don't do it on your training set. So yeah, this is just a fully connected network, pretty straightforward. If you want to get into more deeper nuts and bolts, then snnTorch has a lot of documentation to describe how a lot of these functions, what they're actually doing. So yeah, for example, if you want to look into the details of the mean square error loss, we've got a pretty crappy explanation here. And then not in terms of the computational graph, but yeah, it's very well documented. Finally, I just want to show you the tutorial. So I showed you Google Colab. It's a really neat way to use GPUs if you do not have GPUs. So you can open up this, I guess, Colab notebook, and it basically gives you all the ins and outs, all the finer details of everything I've described. So there's a whole series of tutorials that I've written up. They're pretty good. There's a few pictures in some of them. That's kind of nice. Oh yeah, I've accounted the reset mechanism here. But yeah, so I recommend checking that out if you're interested. I think I've taken up plenty of your time. Thanks for entertaining my voice for like 3 hours. I think we're all sick of it. Those of you in Zoom world, enjoy your nap. I don't know. Oh, I guess I probably forgot to share my screen. Did I? I don't remember. Oh, sick. Okay, you're lucky. Yeah, good. All right, awesome. Yeah, thanks so much for tuning in. Have a good one, guys. Oh yeah, questions, I guess.